In this example, I have this mass, block A, and this block A is sitting on top of this 30-degree incline. And what's happening is I have this 400 Newton horizontal force, which is pushing on this block A and forces it to go 2 meters, go 2 meters. And what I want to do is figure out the total work done by all my forces when this block has moved 2 meters. And the first step I need to do, I need to draw a free body diagram. What this free body diagram tells me is it shows me all the forces that are working on the system, which is my block. And then from these forces, I can determine which ones do work and which ones I can ignore. So if I look at a free body diagram, here's my block. I know it has a weight, and this weight acts directly down, and its weight is equal to its mass, which is 10, times gravity, which is 9.81. I also know that I have this 400 Newton force. These are the easy ones. This 400 Newton force acts completely horizontal and is constant. Now, the third force I have is a normal force. This normal force is perpendicular to the surface that this block is resting on. This is always the case. It's always perpendicular to the surface you're resting on. If this wasn't a 30-degree incline, if this was flat, it'd be straight up and down. But since it's a 30-degree incline, this normal force is at 30 degrees. So this is my normal force. And finally, I have a spring force. And we just have to figure out which direction the spring force is acting. Now, the spring force is stretched, initially stretched 0.5 meters. So when I stretch it another 2 meters, when I bring the block farther up, the spring is going to want to bring the block back down. So my spring force is going to act in this direction right here, because it's going to want to return to its unstretched position. So this is my force of my spring. And now these are all the forces that are acting on my system. I just need to go through, figure out which ones do work. So I have this 400 Newton force, which is constant. And we know a constant force will do work on my system. So I need to account for this 400 Newton force. Now we know a spring force is going to do work on the system because we have an equation for a spring force. So we also know this spring force needs to be accounted for. Now we have the weight and the normal force. Let's talk about the weight first. Now, a weight is only going to do work on a system if the delta y, or the height of the object, changes. So if this was a flat surface, this weight would never do work on the system because the height of this block will never change. However, in this particular case, this height right here is the height that this block goes up. So yes, our weight does do work. Our weight is going to go higher. So our weight is going to do work on our system. And finally, what about this normal force? Well, this normal force is not going to do work on the system, because this normal force is always perpendicular to the direction of motion. So this block is moving up and down this incline, and regardless of whatever position it's in, if it's here, its normal force is perpendicular like this. If the block moves to this point right here, its normal force is perpendicular like this. When it's reached this 2 meter mark right here, its normal force is perpendicular like this. The normal force is always going to be perpendicular, and thus it does not do any work on our system. So we can ignore it when we try to find the total work by all our forces. So now we've found all of these forces, we just need to find the work done by each of the forces. Let's start with this 400 Newton constant force. So for a 400 Newton constant force, our equation is going to be the force times the cosine of theta times S2 minus S1. This was derived in my last video, and this is the force from point 1 to point 2. Now this right here is just going to be our change in distance, because we're going to say at S1 it starts at 0. So at S2 it's going to be this 2 meters we're looking for. So we have a 2 minus 0 times our force, which is 400. And we want the force in the direction of our motion, or the motion in the direction of our force. So if you think of, well, here's our 2 meters going this way, then this angle right here is 30. So it could be cosine of 30 right here, or you could think of it of a coordinate system like this right here. So if this is our 400 Newton force right here, this right here is going to be 30 degrees. The 400 is our magnitude, so we want this part of our vector right here. So again, this is going to be the cosine of 30. And when you do this calculation out, you get this is equal to 692.8 joules. Now, so this is the constant force. Our spring force, we know, is equal to minus 1/2 k times S2 squared minus 1/2 k times S1 squared. And we're given K. We're given K is 30 newtons per meter. So this is equal to a minus 1/2 30. And this is the distance that the spring, the spring is stretched at 2 meters. So if the spring is initially stretched 0.5 meters right here, then we know this spring is going to be stretched this extra 2 meters plus the initial 0.5 meters. So it's going to be a total of 2.5 meters that the spring is stretched in the final position. So that's going to be squared minus the 1/2 30 times the initial the amount the spring is stretched in this initial position right here when we start looking at our system. So it's initially stretched 0.5 meters. And if we do this calculation out, we get this is equal to minus 90 joules. And this should actually be the work from 1 to 2, not a force of a spring. Now we just have to account for our weight, and our weight from the work of the weight from 1 to 2 is equal to minus the weight times our change in height, and this delta y is this right here. So this is going to be equal to minus 10 times 9.81. Our height, we're going up, so this is going to remain a negative because this is going to be a positive value. Our change in height right here is going to be this 2 meters times the sine of 30, and that will give us this distance right here. So 2 times the sine of 30, and this is going to be equal to minus 98.1 joules. So finally, we're going to have the total work of the system. We'll call this UT, is going to be equal to, well, let's rename these. Let's call this right here U sub constant force. Let's call this one U sub spring, and this one U sub weight. So this is going to be equal to the work by the constant force plus the work of the spring plus the work of the weight. So this is equal to 692.8 plus a minus 90 plus a minus 98.1, and the total work of the system is equal to 505 joules.